All right, well, last time we ended up here in section 3.2. And we will try to get through the rest of chapter 3 so that you can work on homework this weekend. We may or may not get through all of it, but we shall see. Not likely we'll get through all of it. Right now we have let's see here. We have homework supposedly due tomorrow, but I don't think that's gonna be very likely that we'll be done with it by then. So let's go ahead and push that till next week. And yeah, we'll deal with the rest of it later. All right. Obviously somebody has sent me some messages that I haven't checked yet.
That was probably me.
That's okay. We'll get to them eventually. Everything's in the wrong place. All right, so anyway, back to chapter 3, motion in one dimension. We talked a little bit about displacement, distance, position, and then we went on to speed and velocity. We talked about the fact that you can calculate instantaneous velocity using calculus, which is really the reason that calculus was invented, was for calculating such things. And in this example here, example 3.3, they actually have given us a function that tells us the velocity of a particle. And the function is a position function. Doesn't tell us velocity, it tells us position. But we can actually calculate the velocity from this position because of this formula here, which tells us that the derivative of the position function is equal to the velocity function, not this one here, actually. It's that's actually just the calculation of a derivative of a polynomial. But anyway, we can actually use this to calculate the velocity function. So we do that down here. We do it term by term. So we do the derivative of the first term. The derivative of the first term is going to, we're going to take that 3 times t, and that's a t to the 1. And we did this last time, but we'll do it again really quick. So that's a t to the 1 power. Get my little drawing tool going here. So this is what it looks like when you take out the units: 3 times t to the 1 power, and then plus, what was it, 3 plus 1.5 t, no, it was 0.5, dang it, 0.5. 3 times t to the 1 power plus 0.5 times t to the 3rd power. And that's our function. And if we're going to take a time derivative of this function, that will give us a velocity function. It'll give us velocity as a function of time. So to do this derivative, we're doing the derivative of this part right here. And we do it one term at a time. And to do that, the polynomial, the derivative of a polynomial, you look at the exponent in the polynomial, in the term here, the exponent of the t. We're going to subtract 1, where we're going to take that 1 down in front, so that it becomes 1 times 3, and then we subtract 1 from it, and put it back up in there. So it's 1 minus 1 up there. You do the same thing on this next one. You bring down the 3, ends up being 3 times 0.5 rather. And then you subtract 1 from the 3 and put it back up there. So it's 3 minus 1 up there, which is going to be 3 to the t to the 2. And that's your function. So to simplify this, you have 1 times 3, which is just 3. And then t to the 1 minus 1, which is 0. T to the 0 is just 1. So this ends up just being 3. Plus 3 times 0.5 is 1.5. And then t to the 3 minus 1, which is t squared. So now this function tells you the velocity at any given point in time t. And all you need to do is plug in a time. They want to do it at 1 second. Let's see, average velocity between 1 and 3 seconds. So we go ahead and do, we can actually do we can actually plug in 2 seconds, which is what they want to do here. So they're plugging in t equals 2 seconds. When you plug in t equals 2 seconds, you get 3 plus 1.5 times 2 squared, which is 4. So 4 times 1.5, which is going to be 6. And then you add those together. And that's what they've done here. 3 plus 1.5 times 2 squared. So this total here, when you do this evaluation, is 9. Going to equal 9 meters per second as the velocity. In part B, they do an average. Now, an average does not require you to use a derivative. You just need to calculate the beginning and the end position and then divide by the total time. That's what they do here. They use the original function. They'll use this function up here, right here, and they'll calculate x at time 1 second and x at time 3 seconds. And at 1 second, they get a position of 3.5 meters. At 3 seconds, they get a position of 22.5 meters. And then they just take the difference between those two, 22.5 minus 3.5, and divide by 2 seconds. Turns out to be 9.5 meters per second. So the average is not the same as the instantaneous, which we would expect. If this thing doesn't have a constant velocity, we would expect the average to be different than the actual velocity. And that's definitely the case there. Here they calculate, they use that position function again to calculate instantaneous velocity at 3 different times. So to do instantaneous velocity, we need to calculate the actual velocity function by taking the derivative and then plugging in the different times. So here's the velocity function, plug in 0.25 seconds, plug in 0.5 seconds, plug in 1 second, you get 3 different velocities, 1.50 and -3. And then you calculate the speed by actually calculating the distance traveled and divide by the, and then divide by the time. Let's see, what do they actually do? What is the speed of the particle at these times? Oh, so in this particular case, they actually just want to know the speed at these times for the particle. So you don't actually, we're not actually doing any kind of distance calculation for part B. But in part B, when somebody says, what is the speed at a particular time, and you know the instantaneous velocity at that time, then the speed is just the magnitude of the velocity. It's the speed is the magnitude of the instantaneous velocity at that time. So it just ends up being 1.5, 0, and 3 instead of -3, because that's the absolute value. Pretty straightforward stuff. And this is the comparison of the 3 graphs. The first graph, being the position versus time graph, looks kind of parabolic, but it's actually not quite parabolic. It's a cube. It's a cubic function, so it's a little bit steeper than parabolic. But you can see that it definitely has curvature to it. There's definitely a changing position that is not simple. And then the velocity curve is going to end up being the derivative of the position. And when you take the derivative of a curve, you're actually getting the slope of it. So here you can see that we have a slope that is positive and pretty steep at the beginning, but then it kind of is not as steep and then it goes to zero. And that's what happens here. So it's positive big number, then a positive smaller number, then zero. Positive big number, then positive smaller number, and then zero. Right to there. And then it all goes negative, just negative, negative, negative. It gets more and more negative as you go on, and that's what's going on here. So, in this one, let's see, is that the actual? So they're actually using a different, this is actually a different curve here. So this is parabolic, not cubic. So but anyway, that's fine. That's why this becomes linear. But if you take the derivative of that function, which is parabolic, which is a quadratic function or a squared function, it will give you a linear function. It will give you a function in t, which is linear, and that's why we get this one. And then if you're going to take the absolute value, then you just take all the negative values in this one and make them positive values. So all this negative stuff becomes positive and goes this way, and that's what this is here. So now we've learned displacement, distance, position, velocity, speed. Now we move on to acceleration. Velocity is the change in the change in position over time, or the displacement over time. And acceleration is the change in velocity over time. So acceleration is another derivative. It's a derivative now of velocity. And the average acceleration, if you want to calculate the average between two different points in time, is really quite simple. You just take the velocity at one point in time, your final point in time, sorry, and subtract your initial velocity from it, and then divide by the elapsed time. So that's pretty simple, very similar to the average velocity. Acceleration is a vector, and it confuses people that acceleration is a vector often, because it has an effect on things that's not completely intuitive all the time. So, for example, here's an example of an object that's moving to the right to begin with, and it has an acceleration that's affecting it, and eventually its final velocity is actually moving to the left. And if you actually do the vector difference here, and you do the vector math of this situation, you would actually find that the acceleration is to the left. This is the case when you have an object that's moving in one direction, has an acceleration in the opposite direction. Eventually, that acceleration can actually slow it down to a stop and then start it going the other direction. So we can end up with a final velocity in the opposite direction from your initial velocity. Let's go ahead and do a calculation really quick with an example. We have a horse race going on here, and the initial velocity of our horse is 0. The final velocity of our horse is negative 15 meters per second. So moving to the left at 15 meters per second. And they want us to calculate the acceleration from this. Well, the average acceleration is going to be the difference in velocities, final minus initial, divided by time. They give us a time of 1.8 seconds, so this becomes a fairly simple calculation. Final velocity is our negative 15 meters per second, initial is 0, so negative 15 minus 0 equals negative 15. Divide that by the time of 1.8, we get a negative 8.33 meters per second squared acceleration. You can calculate instantaneous acceleration just like you can calculate instantaneous velocity. But of course, it's going to require, again, a functional form for the velocity so that we can actually take a derivative of it. So if you have some kind of function that is describing your velocity, you can do this. You just take a time derivative of that velocity function. And again, the time derivative of the function is going to again give us the slope. So it tells us how it's changing, which is what the whole point of the derivative is, to tell somebody how it is changing. So here is a velocity function. This is telling us the velocity of a particle. It is a quadratic function. If we take the time derivative of this velocity function, it will give us an acceleration function. So we go ahead and do that. We take the time derivative of it. The time derivative leaves us with 20 meters per second minus 10 meters per second cubed times time here. The units end up funny just because they have to match in the end, but well, there are mathematical reasons for it too, but it's just you don't need to worry too much about this weird meters per second cubed thing. That's just because we're going to multiply by seconds when we multiply by time here, and it'll end up as acceleration in the end. But once we've got this function, we can plug in different times. If we plug in 1 second, we get negative 25 meters per second. If we plug in for the velocity, for the acceleration, we plug in 1 second, we get negative 30 meters per second squared for the acceleration. If we plug in different times into the acceleration, you will get, of course, different numbers, because the acceleration is changing linearly. It's changing as each second goes on at a pretty constant rate. So you can see here, this quadratic form of this velocity curve is definitely quadratic. It's a parabola. But when we take the derivative of that, we definitely get something linear in the acceleration. It starts off positive, just like this graph starts off with a positive slope. And eventually that positive slope kind of flattens out and becomes less and less positive, and eventually becomes 0 at about 2 seconds, which is right where the peak of that parabola is. Turns to 0, and then it increases it increases in a negative way after it goes through 0. So the acceleration becomes more and more negative after it passes through 0. So different accelerations that are kind of common. A high-speed train has a fairly low acceleration of 0.25 meters per second squared. An elevator, quite a bit higher. Cheetah, a little bit higher still. And this is the acceleration you feel when you fall in Earth's gravity, about 9.8 meters per second squared. Space shuttle maximum during launch is about 29, so it's about 3 times the gravitational acceleration is what a space shuttle went through when it was launching at its maximum. That means that at the maximum acceleration inside of a space shuttle, you would actually feel 3 times as heavy as gravity makes you feel. If you're getting ejected from an aircraft, you're going to be feeling 147 meters per second, which is more than 10 times, almost 15 times the amount of force that you feel from gravity, or acceleration you feel from gravity. So these are all different accelerations. Most of these we don't really experience firsthand, but you can see the baseball struck by a bat is pretty high, 30,000. The proton in the Large Hadron Collider is 1.9 billion meters per second squared. And that's an insane amount of acceleration. And only very small particles can feel that kind of acceleration. Oh, excuse me. So now we've gone through everything: position, change in position, which is displacement, distance, velocity, speed, acceleration. And we're going to make things a little bit simpler as we move on. Instead of having t final minus t initial, we're going to just have t in these equations. Instead of x final minus x0, we're going to have just x minus x0. And same with v, just to make things easy. These things that have acceleration, where the acceleration is an average, we're going to assume that we have constant accelerations most of the time. So it'll just be the acceleration a. This is just to make things easier to write down for the most part. But one of the things that we're going to do is we're going to start combining equations to make some formulas that are useful for us. The objective of this is we're going to try to create a kind of a toolbox of formulas we can use to solve different problems in a much more efficient way rather than trying to figure things out from scratch every time. So this is the first equation. Essentially, they took the definition for the average velocity and they solved it for the initial position or the final position, x. So for motion in a straight line, one-dimensional motion, you can actually solve for the final position if you know the initial position, the average velocity, and the time. Pretty straightforward. Of course, the average velocity can also be calculated. If you take the initial velocity and the final velocity, add them together, divide by 2, that would give you the average velocity. Excuse me. Well, you can do the same thing with the acceleration equation. The definition for acceleration can be solved for the final velocity. You get this equation. Now, these equations really only work, particularly this one, if the acceleration is constant. If the acceleration is changing, these equations don't hold up anymore. So here we're going to use that second equation to calculate the final velocity of an airplane that's landing. Its initial velocity as it's coming towards the ground is 70 meters per second. And then it's going to accelerate with an acceleration that is opposite to its motion. So if it's going 70 meters per second in the positive direction, then the acceleration is going to be 1.5 meters per second squared in the negative direction. It's going to do this for 40 seconds, and we're going to find out the final velocity by using the equation right here. V final equals V initial plus acceleration times t. Remember, your acceleration needs to have the correct sign. In this case, in this problem, the acceleration is negative. So there's our values, the parameters that we're going to use. We're going to put them into this equation and solve for the final velocity. Turns out it's going to be a final velocity of 10 meters per second. Now, here's another thing that we can do. We can take that same equation and we can actually add V naught to both sides and then divide by 2 on both sides, and it gives us this equation. Kind of like a little bit of algebraic voodoo, but it still works. What this gives us is on the left-hand side, you can see that we obviously have the average velocity here. And so we can actually replace it on the left side with the average velocity. And then we can actually replace this average velocity on the left-hand side with the average velocity solution from the first equation we built. And that actually gives us this equation, which is a much more complex equation. It has a time in it, has time squared in it, has acceleration, initial velocity and position, and final position, but still a very useful equation. Each one of these equations is like a little tool that we can use to do these different homework problems and solve different problems in physics. So this is another one of these equations that also assumes that we're using a constant acceleration. So we're going to go ahead and use that in this example here with a race car. We've got this drag racing car, and it is going to be accelerating with an acceleration of 26 meters per second squared. And they're going to tell us that it's going to start from rest, which means our initial velocity is 0. And we're going to assume that our initial position is 0. We're going to try to calculate how far it's going to travel. Well, in this equation here, we can find the final position if we know initial position, initial velocity, time, and acceleration. And we know all those things. Turns out the initial position and initial velocity are both 0. So these first 2 terms go to 0, and we just are left with this equation, very simple formula. Plug in our acceleration, plug in our time, calculate 402 meters, which is just about right for a drag race. Then there's one more thing we can do. We can actually take our velocity equation, solve it for time, and then take our average velocity equation and plug those both into the first equation, which was our equation for position, or our average velocity equation at the very beginning. And then if we put all those together, we actually get this equation, which is again fairly complex equation, but it's useful because it can tell us the final velocity if we know the initial velocity, the acceleration, and the distance traveled. We don't even have to know time for this equation, which is really nice. So we can solve for something, and this again assumes we have a constant acceleration. And we actually do this with the drag racer again, but this time we're going to calculate the final velocity of the drag racer by plugging in the initial velocity, which is 0, the acceleration of 26.0 meters per second squared, and the total distance traveled, or x minus x naught, which is 402 meters. Plug all those in, calculate, and we get a velocity of 145 meters per second, which is easily reasonable. It's about 300 miles an hour. That's pretty normal for a drag racer. In fact, that's pretty low, a little low for a drag racer. Excuse me. So if we compile all these equations together, we call them as a group the kinematic equations, or the equations for measuring movement, which is what kinematics means. The mathematics of one-dimensional motion. Now, essentially the rest of this chapter is doing different problems that use this. So as long as you're in straight line motion, you can use these equations to solve for different things of interest, for the distances, for the velocities, for the accelerations, whatever, the time that it takes to do things. As long as you're in one dimension, you can do this. Now, one other caveat is you do have to have a constant acceleration when you're using these equations. But as long as you have those two things, you're in one dimension and you've got no external forces and only one constant acceleration allowed, essentially. No changing acceleration and no other accelerations involved, then you're good to go. Here they do an example of a car stopping on wet pavement and dry pavement. So they give us two different accelerations. For the dry pavement, they give us an acceleration 7 meters per second squared, and it is opposite. This acceleration is in the opposite direction of the movement of the car. And then for wet concrete, they give us 5 meters per second. And you can see here the drawing. Here's the car. Here's the distance that it's going to stop in. Initial velocity 30 meters per second, final velocity 0. We want to calculate the distance it's going to take to stop using these numbers. Well, the last equation, the last kinematic equation, turns out to be a good one for that, because if this is an equation that tells us if the distance, which is x minus x naught, if we know the acceleration and the initial and final velocities, which we know both, we know all that stuff. For this car, the final velocity is 0 because it's coming to a stop, right? So final velocity is 0. The initial velocity is going to be whatever initial velocity the car has in the problem. In this case, it's 30 meters per second. So that's simple. And then knowing the initial and final velocities, all you need to know is the acceleration. They did tell us those two accelerations. So what they're doing here is they've solved this equation for x minus x naught, which is the thing that we want to know. And notice they haven't plugged any numbers in yet. Again, that's really important. If you plug in the numbers and then start solving the equation, it can be really easy to make mistakes. I highly recommend that you solve the equation before you plug in the numbers, and then you can use this as a formula several times if needed. In this case, you definitely need to. So we solved this problem with dry concrete, an acceleration of 7 meters per second squared. Notice that they plug in a -7 because the car is moving in the positive direction, and it said that the acceleration is in the opposite direction, which is negative. right? And that's usually what happens when you're trying to slow something down. The acceleration is in the opposite direction of the movement of the object. So there's -7 in there, and then they plug in those numbers and calculate. So on dry concrete, it's a 64.3 meter stopping distance. But the interesting thing is the next part says we want to do this for wet concrete. It's a different acceleration, but all you need to do is go back to this formula and now plug in the numbers, replacing the acceleration at -7 meters per second to -5 meters per second squared. Because you've already made the formula, you only need to do it once and you're good to go. Now, in the last part of the problem here, they say, well, this only accounts for after you've hit the brake. What if there's a little bit of time delay between seeing the light turn red and hitting the brake? Then how far would the car travel? Well, before you actually hit the brake, the car just travels at normal. So if it's moving along at 30 meters per second and it takes you a second to hit the brake, it's going to move 30 meters before the brakes, the car starts stopping. And then after the brake has been applied, you'll use the numbers from the previous parts. But that's what they do here. They take the reaction time and calculate the distance that the car travels in that reaction time. And then they add that reaction distance on to the two distances that the car traveled, the 64.3 and the 90, in dry and wet conditions. And they get new answers of 79.3 and 105 to calculate those final stopping distances with that extra time. Here they have a car that is merging onto the freeway, so it's speeding up along a 200 meter long ramp. They tell us the distance that the car is going to travel. They tell us the initial velocity, and they tell us the acceleration. They want to know how long in time it's going to take for the car to go up this ramp. Here's the drawing of it, all the stuff that we know, the things we want to know. Looking for an equation that will help us to solve this, we find that the quadratic equation is the one that's going to tell us the time with the things that we know, which is a little bit unfortunate because when you're solving this equation for time, you end up with a quadratic equation. Solving quadratic equations is not necessarily fun. In this case, they just plug the numbers into the equation and then they rearrange the equation to be in standard form. So they also get rid of the units and all the decimals just to make it simple looking. So this is what it looks like in simple terms. But then they're going to go ahead and subtract 200 from both sides and then divide by, actually they don't have to divide by anything, but then they just rearrange from the highest order to the lowest order to get the standard form for a quadratic. So it's t squared plus 10t minus 200. And then you use the quadratic formula. If you don't remember the quadratic formula, they have it written down here where a is the term in front of the t squared term, which is 1 in this case. B is the coefficient in front of the t term, which is 10 in this case. And C is the constant term, in this case, -200. Remember, the sign to the left of every number goes with that number. So in this case, C is equal to -200. Then you plug it into this formula and you can see there's a plus or minus in here. So we're going to get two answers. The two answers end up being 10 seconds and -20 seconds. Well, the 10 seconds has to be right because something that happens -20 seconds would be 20 seconds before the experiment started. So we don't use negative times in physics for the most part. And in this case, the correct answer is when at time equals 10 seconds, that's when they finish accelerating up the ramp. So it takes 10 seconds for this car to get up onto the freeway. Here we're going to do an acceleration of a spaceship. So they tell us the acceleration, they tell us the time, they tell us the distance. Once again, so we're going to use that same equation, but this time we're going to actually calculate the initial, let's see here. Yeah, in this case, they're going to use this equation with all the stuff that they gave to calculate the initial velocity. And then once they know the initial velocity, they're actually going to solve for the final velocity using one of the first kinematic equations, and then solve for that final velocity and get it there. So sometimes you're going to use more than one of these equations to solve one of these problems. But it's not really very difficult. You have essentially 6 equations, 5 really, but you have these equations, and you're going to look at different situations, and you're going to say, okay, which equation is going to give me what I want using the stuff that I have? And you might have to use one equation to get some other value, and then use that value in another equation to get your answer. But using multiple equations is something you should be used to. So going back to the kinematic equations, these are things that you should highlight. You'll use them regularly, and you'll use them quite often, and you'll use them a lot. But these are your equations. There are these 5 kinematic equations. Each of them gives you a slightly different piece of information using slightly different information. You can use them together, you can use them separately. The kinematic equations. And remember that the kinematic equations are only good when the acceleration is constant. You have to have a constant acceleration to use these equations effectively. Okay. So section 3.5, which is nearly to the end, is free fall. In free fall, you're just dropping something, and the acceleration in free fall is known. Assuming there's no air friction or anything slowing down an object in free fall, then the acceleration is equal to 9.8 meters per second downwards towards the center of the Earth. And since we normally consider up to be positive, then that constant acceleration from gravity would be equal to negative 9.8 meters per second squared. So that's usually the case. What I mean by, air friction or something like this, this is something that's easily demonstrated here on Earth. If you drop a hammer and a feather or a piece of paper or something big, something heavy, and something fairly light that has its area spread over a big area like a feather or paper. You drop a hammer and a piece of paper together, the hammer is obviously going to hit the ground first. And that's because the weight and the aerodynamics of the hammer allow it to overcome any kind of forces from the air friction in the air. Whereas a paper is very lightweight and has this huge surface area, so it essentially is affected a lot by this air pressure upward, or this air resistance upward. So when they went on the moon, I think it was Apollo maybe 14, 15 or something like this. They brought a feather and a hammer and they dropped them on the moon where there is no air. And lo and behold, they fell at the same rate and both hit the ground at the same amount of speed. It's not showing up on that. I lost my mouse. There it is. All right, so if this is our new acceleration g, and we consider it to be negative and pointing in direction, we can actually change our kinematic equations. All the equations that have acceleration in them now have negative g in them, and they change like this. You can also just leave them as they were before, and that's totally fine, and just plug in negative 9.8 for your acceleration, which is actually what I do. But you can also change them slightly and have them turn out like this. They've also replaced x with y, because we usually consider the vertical direction to be y or z or something like this. So they've just replaced x's with y's, and then the accelerations with negative g's, and that's fine. Just make sure that you either decide if you're going to use these equations. The negative in front here implies that you've already plugged in the negative, so g is just equal to 9.8 in this case. Whereas if you use the equations we had before and just leave all the accelerations as a's, there will be positives in front of all those A's. And so you need to actually plug in negative 9.8 for your acceleration if you use the previous equation. Doesn't matter one way or the other. If they have a ball, they're going to drop off a building, and they're going to calculate the different velocities at different times and the different distances it's traveled, but you're just using these equations again. At different times, you're plugging in different values for your initial velocity, your final velocity, your initial position, whatever information they give you, and you're going to use that to calculate other pieces of information. Totally straightforward, simple. The interesting thing about the dropping the ball experiment is you can actually do a throwing of the ball up experiment, and it behaves the same way as the dropping ball experiment, except that when you throw the ball upward, the downward acceleration from gravity at first is just going to slow that ball down to a stop and then accelerate it downward. So it does some slowing down and then to a stop and then turns it around and it comes back down like a dropped ball again. But the math knows how to do this, not a big deal. The math can handle it no matter which way the initial velocity is, or if it's just zero. So in the case here, they throw the ball straight up and they want to know the final velocity of the ball after 5 seconds. So they use this equation again, this quadratic, and they know the time, it's 5 seconds. They know the initial velocity, they know the final velocity is 0 because they want to find out how long it takes to get to the top of its motion. And when an object that is in free fall, or it's in the gravitational field, when that object reaches the top of its motion and it's about to turn around and come back down, its velocity in the y direction is 0 when it's stopped. When it's turning around, that turning point from going up to going down is always a velocity of 0. So their final velocity is known here. So right here, their final velocity is known. They're also assuming, I think, that their initial position is 0. Yeah, their initial position is 0. And their final position is also 0. So they're going to actually count it or catch it when it comes back to where they threw it from.
This might be an odd question. So like you said, when a ball or like something is tossed up in the air and it like reaches the highest point and it's like acceleration's like briefly at 0, is that always like the same amount of time that its acceleration's at 0? Like how long before it starts falling again? Or
so a quick correction, at the top of the motion, the acceleration is actually still negative 9.8 meters per second squared. It's the velocity that is 0 at the top.
Okay, velocity.
Because it comes to a stop. In order for it to turn around, it has to come to a stop, and then start going the other direction. Anything that changes direction has to come to a stop in that direction before it turns around and goes the other direction. So it's the velocity that goes to 0 at the top of the motion. The acceleration is still negative 9.8. It's negative 9.8 the whole time, whether it's moving one direction or the other direction or stopped. The acceleration is always the same. Now, you say, how long does it stop for? Is that the question you're asking?
Yeah.
Yeah, everything that goes from going up to going down and stops at the top of that motion is always stopped for the same amount of time, and that amount of time is 0 seconds. It has a stop time of absolutely no time. So it immediately goes from going one direction to the other direction without spending any time up there. Now, that doesn't seem that way. For example, athletes talk about hang time, and it doesn't seem like it's no time at all that it's been stopping, because right before it stops, it's going super slow, right? Because it's slowing down, and then it stops. And then right after it stops, it's slow again. As it slowly speeds up again, it's slow again, right? So there's this drawn out time when it's going really slow, and then it stopped, and then it's going really slow again. So it seems much longer than it is. It's actually stopped for 0 seconds, 0.00 absolute 0 seconds. But the time it spends going very slow is maybe a fraction of a second.
So we kind of, our eyes kind of trick us into thinking that it's stopped for a little bit longer than it actually is.
That is correct. You can't actually detect it when it's going very slowly. You can't detect its movement, so it seems like you're kind of hanging there. And then that's where you get the whole cartoon thing. You get the road runner going off the edge of the cliff and standing there in the air. When in reality, something goes off the edge of a cliff and immediately starts to accelerate downward off the cliff, right? So, yeah, it's definitely a trick of the eyes and the mind, but it's still cool to watch. It was I can tell you the really interesting thing is the more that you're moving sideways while you're moving up and stopping and turning around and going back down, the more this effect is drawn out. So this is one of the reasons Air Jordan got his name, Air Jordan. He was very famous for having a very broad jump dunks in basketball. He could jump something like 17 feet from the hoop and still dunk the basketball. I think that was his record. So he was beyond the free throw line. Well, that actually meant that he was moving so much sideways that he would actually look like he was moving flat across the sky, kind of straight across the air, and made it seem like he was hanging in the air for all this time, when in fact basketball players can only stay in the air for about a second. Really good basketball players, 1.1, 1.2 seconds is the maximum amount of time they can stay in the air from the time they jump to the time they land, is only about 1.2 seconds, 1 point something seconds. It has everything to do with how high you jump, not with how broad you jump. How broad you jump affects how long you're in the air, not at all. The only thing that affects how long you're in there is how high you jump. And Michael Jordan had a really high vertical, something like 50 inches, which is much higher than most basketball players ever reach. Most basketball players can't go above probably 35 inches or something like that. The highest jumping basketball player ever was probably one of the shorter players that could dunk, had like a 54-inch vertical or 56-inch vertical. But it didn't look like he was jumping for very long in the air because he had to jump straight up to get there. He didn't have as much of a broad jump ability. So Jordan could waste energy and jump a nice long broad jump. If you compare to other sports, the highest jumping athletes in the world are all high jumpers. They're all on the track teams jumping the high jump, and they can stay in the air for about 1.5 seconds. Probably the best of them. Volleyball players, men's volleyball players can jump for about 1.3, 1.4 seconds. They're usually about as tall as basketball players, but they're usually 50 pounds lighter, so they can jump a lot higher. On average, their jumps are quite a bit higher than your average basketball players. Weightlifters can jump really high. Weightlifters tend to be short and stocky people, but they have extremely fast twitch muscles, so they can jump usually 40, 50 inches. You can usually dunk a basketball without running. Kind of crazy. Anyway. Interesting question. Thank you for your question. So that actually takes us to the end of the class for today. There is one more section in the class, which is finding velocity and displacement from acceleration. We will go ahead and cover that last section on Monday when we come back and finish up chapter 3 then. Have a good weekend though, and we will see you next week.
Have a good weekend.
Thank you.
Will you record Monday too? I'll be gone for a college visit.
Yes.
Okay.
I will record this class every day.
Okay, perfect. Thank you.
Yep.
And then I wanted to tell you that I turned in my application yesterday for QWIP.
Oh, excellent.
Yeah.
I hope
Thank
that
you for
get
sending
it.
me that email.
Oh, it's my pleasure. We'll see you later.
All right. Have a good weekend.
Yep. In case you're wondering why you all didn't get the same email that I sent her, it's a women's conference for physics. Only women are allowed. Yeah, it's a big conference they have every year, actually, and it's completely paid for except to get there. So you get there, if you apply and you are selected to go, they pay for you to go to the conference and they pay for your room and board and get to learn about being a physicist. But it's only for women. Excuse me. Have a good one. We'll see you later.